The first ace. Shuffle an ordinary deck of 52 playing cards containing 4 aces. Then turn up the cards from the top until the first ace appears. On the average, how many cards are required to produce the first ace? Let's look at a few possible solutions to this problem. One solution uses an indicator variable approach, which goes as follows. First, since the problem states that the cards are shuffled, we expect the aces to be uniformly distributed across the deck. So let's visualize these cards. Here the 3 dots represent the non-ace cards, and the letter A represents an ace card. Note that these aces act as separators for non-ace cards, and they divide the deck into 5 parts. Because we need to somehow count the cards, we create an indicator variable which we'll call xi. And xi is going to take a value of 1 if the card it represents comes before all aces. And it will take the value of 0 otherwise. Now, because we need to count the number of cards to produce an ace, we need to create another variable, let's call that n, which is going to be the sum of xi. Here, the index is going to run from 1 to 48 because we have 48 non-ace cards. However, we also need to add a +1 because we need to count the ace itself as well. Now we need to take the expected value of n. Here, expectation value of 1 is just 1, and then we have expected value of this summation. Now we use the linearity of expectation property, which tells us that the mean of sum is the same thing as the sum of means. In other words, we can just take the expectation value inside the summation. Now we need to find what is exi, and this is the key part here. Note that the indicator variable xi takes the value of 1 only if it comes before all the aces. That can happen only in this first lump. Also, by symmetry, we can say that this first lump of non-ace cards is equivalent to the other lumps. So we have 5 of these parts, and only in one of them, which is this first one, xi takes the value of 1. That's why we can say that the expected value of xi is 1/5. So here, we just need to substitute 1/5 to exi, and since this runs from 1 to 48, the answer becomes 1 plus 48 multiplied by 1/5, which is equal to 53 divided by 5, and this is the answer. Now, there is another approach which doesn't use an indicator variable, but relies on symmetry arguments. In this case, we say, okay, we have 48 non-ace cards, and because we have argued that these 5 parts are symmetric, we can directly say that the expected length of this first non-ace lump is 48 divided by 5. And then we just need to add a +1 to count the ace. That again gives 1 plus 48 divided by 5, which is 53 divided by 5. By the way, there is another variation of this symmetry argument. In this case, we want to count the lumps such that they include the ace as well. So if you look at this first part here, we have some non-ace cards followed by an ace, another non-ace cards followed by an ace, etc. In total, we have 4 of those. But the issue is that when we come to the last one, we only have non-ace cards. So to fix that, we are going to put an artificial additional ace in there, such that it becomes symmetric with the previous 4 lumps. With the addition of this card, now we have a total of 53 cards in the deck. And because we now have 5 symmetric parts, we can directly say that the number of cards to produce an ace is 53/5. So all of these solutions give the same answer, but they have slightly different approaches. In this case, the symmetry argument gets you to the answer much quickly, but the solution with the indicator variable can also be helpful in similar problems.